Okay, section, well, it's 1.2 and 1.3. They have properties in both. So I thought I would just put all the properties together and kind of just deal with it all at one time, okay? So this has a little bit of 1.3 in there as well. All right, commutative property. Oh, yeah, these are words you've had since like 7th grade. And I know that it's nobody's favorite thing to do, but we got to go through them. Okay, so the commutative property of addition, A plus B equals B plus A. An example of that, we all are kind of aware. 3 plus 4 is the same as 4 plus 3. All right, that's commutative property. In my mind, I always say 3 and the 4 commuted. You commute to work, you go back and forth from work to home, work to home. You guys commute to school, that means you drive from school to home, school to home. So here, 3 went where the 4 was, and 4 went where the 3 was. They're commuting back and forth. Okay, 5 plus 2. Well, they commuted. Now the 2 goes to where the 5 is, the 5 goes where to 5 plus 2 equals, oh my gosh, I had that wrong. 5 plus 2, they didn't commute. It must have been a snow day. 2 plus 5. All right, same with multiplication. The only difference is you have a multiplication symbol. 4 times 5 is equal to 5 times 4. They commuted back and forth. 3 times 7 is the same as 7 times 3. Associative property, okay? When you associate with somebody, you're often talking or chit-chatting. That's always kind of my example. Like, Alice is talking to Betty, and Carl feels left out. Well, then later, Alice is left out, but then Betty tells the secret to Carl. Okay, let's do some numbers. 3 plus 4, and then you add the 5 later, is the same as taking 3 plus 4 plus 5. It doesn't matter if you add these two first, and this only works for addition, by the way, or if you add these last two, as long as it's all addition. You're going to get 12 equals 12. So this is the associative property for addition. Let's look at multiplication. The same thing. 3 times 4 in parentheses times 5 is going to be the exact same value as 3 times 4 times 5 if you multiply the 4 and the 5 first. Let's check. 12 times 5 is the same as 3 times 20. Yeah, this is 60 and this is 60. All right, identity property. Addition. Okay, identity means you keep your identity. It doesn't matter, I'm Mrs. Talley. It doesn't matter if I change rooms. It doesn't matter if you add 14 to me, I'm still Mrs. Talley. And that's kind of the same thing here. Adam plus 0 equals Adam. Or 0 plus Adam equals Adam. It doesn't matter which way you do it. 5 plus 0 equals 5. The 0 does not change the identity of the 5. Or 0 plus negative 2 equals negative 2. Notice how negative 2 keeps its identity. It also works in multiplication. It does not work for subtraction. It does not work for division. So if you take any old letter or number, 17 times 1, you get 17. Notice the multiplicative identity is 1. The additive identity is 0. Okay? So if I were to be multiplied by 1, I would still be Mrs. Talley. All right? Or you take 1 times 17, and you're still going to get 17. Okay? The multiplicative identity keeps the value, and the additive identity keeps the value as well. Okay, the inverse property. A lot of times we think of this as opposites, although if you were in Algebra 1, I'd probably let you get by with that. We're in Algebra 2, you're going to take MCAs, ACTs, all that good stuff. We need to get our vocabulary kind of straightened around. So we probably have called it opposite in the past, and over here the multiplicative inverse would be a reciprocal. Okay, just so those are words that you're much more familiar with. So let's look at addition, the opposites. 3 plus negative 3, you all know by looking at that you're going to get 0. Negative 5 plus 5, you're going to get 0. Okay, we would call 3 and negative 3 opposites. Technically, it's an additive inverse. Okay, it's the inverse property. All right, multiplicative inverse is known as our reciprocal. So 3 times 1/3 gives you 1. Or you could take 1/5 times 5, it'll give you 1. All right, that's your reciprocal, or 3 1/3 reciprocals, otherwise known as multiplicative inverse. Okay, notice I just have to point out this little piece here. These comes out to be zeros, and these come out to be 1. Oh, isn't this your additive identity, and this comes out to be your multiplicative identity? Just kind of a cute little thing you might want to be aware of. Distributive property. This one, I feel confident everybody's got it, but let's just quick say it again. A times B, and then you take A times C. You're distributing papers or candy or whatever it is to everybody in the group. And it doesn't matter if you have like 4 things or 3 things or 7 things in your group. You would take 3 in this case times everything in the parentheses. So you'd have 3x plus 3y plus 3z. Okay? And you very seldom see it like this. Most kids will want to rewrite this, and that might be you. But it doesn't matter. Isn't this kind of like a number? It could put an x in here, and you're taking it times a. It doesn't matter if it's xa or ax. Basically, order doesn't matter in multiplication, but let me just show you here. They took b times a, and then they took c times a. Okay? So let me give you a number one with this. If you had x plus 4, and then you had a 5 out here, I have a sneaking suspicion most of you would put the 5 out front, and that's okay, and then you would distribute. If not, you would do 5x plus 20, because you would take, or you can think of it like this, 5 times the x, 5 times the 4, which is exactly what's happening over here. Okay, so don't let that, every once in a while you get that on a homework assignment, and kids will be kind of freaked out, like, ooh, that doesn't look the way I like to look at it. Well, then in this case, you can change it. Reflexive property. Oh yeah, this kind of reminds you of geometry and proofs a little bit, doesn't it? The simplest example is Q equals Q. Basically, whatever you have written here would be the same as anything over here. So you would write 5 plus 4, reflexive. I always think you look in a mirror. Don't get too technical. If Mrs. Talley looks in the mirror, who does she see? Mrs. Talley. Okay? It would be a little weird if I saw Mr. Talley in the mirror when I was looking in the mirror alone. Okay, that's just freaky. All right, so if Joe looks in the mirror, who's he going to see? Joe. So that's why I have the very exact same thing on both these. All right. Symmetric. I always remember when I was a kid, we would do these things where you would put, well, I don't know always, but we would do like paint here and then paint over here. And then you fold the paper in half, guess what happened? You had the paint over here and the paint over here. So what was on the left side ended up on the right side, and what was on the right side ended up on the left side. Okay? That's what's happening here. Isn't this on the left? Over here it ends up on the right. And this was on the right and now ended up on the left. Okay? And this is easily confused with some other property. I have to think. Oh, commutative. This is not commutative because of the equal sign in there. Well, commutative property, let me clarify. Commutative property would be 3 plus 4 is equal to 4 plus 3. That's it. That's all you got. Okay, where symmetric property, you have like an entire mathematical thing here equal to another one. And then always that if-then statement kind of gives it away too. All right, here's another one. 3x minus 1 equals 7. Then 7 equals 3x minus 1. Okie dokie. Transitive problem. I always think you translate from one language to another, or it translates, kind of like rumors or gossip. It goes from one to the next to the next. So if A equals B and then B equals C, then A equals C. All right. So 2x plus 3 equals 5. Okay, and then 5 equals 4x minus 1. Aren't I saying, I'm going to kind of cross this out. Aren't I saying then that 2x plus 3 equals 4x minus 1? Sure. Then you just write out, oops, the 1 is missing over here. So 2x plus 3 is equal to 4x minus 1. It's just rewritten again. Okay, let me try another one. If 4x is equal to 7, and 7 is equal to 3x plus 20, okay, then, okay, these 7s are the same. Basically, I'm saying then 4x is equal to 3x plus 20. Okay? It went from 4x to 7, and then the news went from 7 to 3x plus 20, and so therefore the 4x is equal to 3x plus 20. Something else I'm thinking about with that. I always say if you know that Joe got 87% on his test, and Billy got the same thing as Joe, and you could go crazy with this. And then Sally got the same thing as Billy. Well, what grade did Sally get then? Well, most of us know we got 87%. It's a version of basically a transitive property. It's translating or being sent through all of those. Okay, and substitution. And this is one thing where maybe, hopefully if you held on to anything out of proofs, there was a section like when we did algebraic proofs and you're like, what? Mrs. Talley, I thought the word proof would never be used again. Basically, you just simplify. I remember we would talk about this. You'd be like, every time you think substitution, you're actually putting down, or you would think simplify, you're actually putting substitution. Because what is 7 minus 2? 5. So we are substituting 5 in place of the 7 minus 2. So if you have, let's do 10 plus 4q is equal to 72, then what is our substitution? Instead of writing 10 plus 4, I'm going to write 14q is equal to 72. And I think most of the time when we do that kind of math, we actually think to ourselves, simplify, but this would be substitution technically by the book. All right, and that's the end of that lesson.